Nothing else much new to say today in terms of announcements. Just keep up the good work on the ALEKS. I believe we are still on the vector applications module. If not, the polar module open. I think that opens tomorrow. Not positive, but just keep up working on your ALEKS modules. Today is going to be the last day we're going to cover any new content. Tomorrow we will be doing a lot of review. In particular, I want to focus on a lot of inverse functions tomorrow because I know those are incredibly difficult. But tomorrow the main focus is going to be review. And then today we are just going to wrap up course content, which is going to be with graphing polar coordinates. Again, I do not think there is an ALEKS module, particularly on graphing. I don't think I enabled those, but this will be useful for the written homework and the exam 3 and potentially the optional final exam. I will go over the announcements again regarding all of the logistics with those tomorrow, but in the meantime, does anybody have any questions on anything?
What day was the optional final exam again?
Optional final will be Friday. So exam 3 is going to be on Thursday this time, unlike the other ones, so that the optional final can be Friday. So if you don't want to take that, you can just be done Thursday, but the optional final will be all day Friday and it will run as a 90-minute exam like the other ones have. All right, any other questions? And I will go over more logistics with that.
On the optional final, if that score is higher than your lowest when it replaces it, but if that score happens to be lower than your lowest previous exam, does it still replace it or not?
No. So say you got a 60, 70, 80 on your 3 exams, but then you get a 50 on the optional final, that will not hurt you. That will not touch your grade. So taking it cannot hurt you. There is no way that you take the optional final and have it hurt your grade. It can only help you. If that's your question. And I will go over that more again on Wednesday, which is tomorrow. Okay. Are there any more questions right now? All right. Well, if there's no questions, we'll just hop into what we're going to do today, which is just graphing, but instead of working in rectangular coordinates, or sometimes they're called Cartesian coordinates like we've been used to, we're just going to practice graphing in polar coordinates. So I will go ahead, share the slides. Okay. So this is where we left off last time, and this was just working on graphing extremely simple polar equations. Just by looking at them, we identified that, oh, the equation r equals 2 is just a circle of radius 2, makes sense. And the equation theta equals pi thirds is just a line through all of the points of with an angle pi thirds. So that one just ended up being a straight line, and r equals 2 just ended up being a circle. Now, we're going to shift gears from this a little bit. We're not going to look at these types of equations. We're more going to look at types of equations that involve trig functions and how we graph those. And we're used to, especially in rectangular coordinates, not looking at particular points, but looking at, okay, here is my parent graph. How can I transform it? There are parent graphs for polar equations, but there are many, many more of them, and they're a lot harder to memorize. So we're more going to focus on what we were doing last time, which is plotting points and then learning how to draw the line from there. So here I have plotted the points for the graph r equals 1 minus 2 cosine theta. That is the points that are plotted over to the right here on these axes. What we want to talk about is how to connect them and how to draw them and how to make the line. Because how do we connect them? Do we do this? Because that is different from this, is different from this, is different from, how do we connect these points? So basically the main way to do it is you're always, always, always going to draw counterclockwise, and you are going to start with the lowest theta value and work your way up. So how should we start drawing? Well, our lowest theta value of all of these ones given to us here is 0. So we're going to start here. That's going to be the first point we plot, and then connect it to point 2 and 3 and 4. So let's start by doing that. The first point is the point theta is 0. So we're not going to rotate at all. We're going to be somewhere on that line. Theta is 0. And then our radius is -1. So we're going to move back to -1. So that's this point here. That's our starting point. And then our second point is pi over 6. So we would rotate out to pi over 6. Oopsies. And then why is it? Okay, go up to pi over 6. And then the point is 1 minus square root of 3. Notice on our R axis labeled over here, we have the point 3 minus square root of 1. So to negate that, it's 1 minus square root of 3. So the negative of this is 1 minus root 3. So we want to go, instead of going forwards to that, we want to go backwards to that over here. And we've already rotated out pi over 6, so that is this point. We rotated pi over 6, so we're working on this line here. And then we go back root 3 minus 1, or -1 minus root 3, because you can rewrite that as negative of square root 3 minus 1. And that point is square root 3 minus 1, so we just go negative in that direction. It's like if our radius was -1, we just went back the opposite direction from the labeled point here. Okay, so we connect these two dots. You can kind of see the next one is pi fourths, so it's going to be on this line somewhere. And again, we can explain that this is the negative of square root of 2 minus 1 as what is labeled on the axes. And we can see it's on that line of pi fourths, just going in the backwards direction. So connect those two. And then lastly, pi thirds is at 0. We didn't even, you can tell this isn't rotated pi thirds at all because it's just at the origin, but any point whose radius is 0 is just going to be on the pole or the center. That's that. So that's the start of this graph, is this little curve here. Okay, now we're to the next point we need to think about connecting the dots of. Well, the next lowest value for theta we have is pi halves. It's a natural progression from pi thirds to pi halves, just like on the unit circle. So the next points we are going to label are going to be these 5. So when theta is pi over 2, so we're going to be lying on this line, r is going to be 1. Conveniently, that is this point right here. So we're going to go up here. When theta is 3 pi fourths, so we would rotate out 3 pi fourths. So we're going to be somewhere on this circle. Our radius is 1 plus root 2. So we go out to the radius. We go out to our radius of 1 plus root 2, and then we walk around the circle 3 pi fourths. So we're going to connect that to that one right there. Even though these are written as theta r's, as you can see, it's a little bit easier to say, okay, what's my radius? I'm going to walk out my radius, and then I'm going to rotate that angle in the counterclockwise direction. So let's keep doing it that way. At pi, we have a radius of 3. So we walk out to our radius, oopsies. We walk out to our radius of 3 right here. So we know we're going to be somewhere on this circle. And then we just walk around pi, and there's the point. So connect it to that one. 5 pi fourths is at the radius of 1 plus root 2. So we walk out to 1 plus root 2 and then walk around the circle 5 pi fourths. There's that point. So these two connect. And then at 3 pi halves, we've walked out a radius of 1 and then go around 3 pi halves to that point. So that's what our graph looks like so far. It's kind of like a little spiral. We can kind of imagine how it'll end, but let's just walk through it very carefully just to make sure that we understand what's going on. The final 3 points, it's the natural progression to go from 3 pi halves to 5 pi thirds, as we can see down there on the circle. So these are going to be our final 3 points. At 5 pi thirds, we have a radius of 0, so that's just going to be back at the origin because radius of 0 always lands us at the origin. At 7 pi fourths, we have a radius of 1 minus root 2, so we go out to that 1 minus root 2 point and then rotate around 7 pi fourths, so that would be like that. So we go to this point, and then our final point is here. And then at this point, the graph would start repeating. if we plugged the value 2 pi in for theta, 1 minus cosine of 2 pi, or 2 cosine of 2 pi, the cosine of 2 pi is just 1. So 1 minus 2 times that is equal to -1. And as you can see, at 2 pi, we would be going out a radius of -1. So radius of -1 at rotation 2 pi would land us there. And the cycle of this graph would just start repeating like so. So just like rectangular coordinates, these graphs repeat too, not necessarily in the period of the graph. We have to be careful with that. It doesn't always necessarily repeat nicely with the period like it does in rectangular coordinates, but when we will always hit a point where we start cycling through and repeating like that, and that is where you know the graph is complete. Even though we didn't graph every potential theta we could plug into there, we have, because it'll just start repeating in that fashion. And as soon as you see the dots connect like that, or things starting to repeat again, you can stop graphing. And we'll see a couple more of examples of how that will work with different shapes of graphs here in a minute. But just for this, are there any questions on how we connect the points? Rule of thumb, you will always, always, always be drawing counterclockwise. And if you can't remember that, just remember, okay, I need to just draw in order of ascending theta values. So I start at 0, and then I draw to the dot at pi over 6, and then I draw to the dot at pi over 4. Because we're not going to be ever thinking about parent graphs with these. We're always pretty much just going to be plotting points and connecting the dots. So you can just think about, you have to go in ascending order of theta. So sometimes it's easiest to draw the line as you go, or just make sure you're always drawing in a counterclockwise fashion. Questions on this? Okay, then let's try an example. I just want to graph r equals 2 sine of 3 theta. That's all I want to do. Well, this over here to our left, the one in rectangular coordinates, is the graph of y equals 2 times the sine of 3x. So we can actually use this to graph the one on the right. We can extract points from it. We can extract coordinates in order to graph our little function on the right, which will be incredibly useful. So how do we do that? Well, we just say that our thetas, our x-axis is now the theta axis, because you can see we're working with different angle values down here. And then the y-axis becomes our r-axis. So you'll notice they get a little bit flipped because we write polar coordinates as r comma theta. So it's a little bit counterintuitive, because we have what's usually in the x slot is what's now on the y-axis, and what's usually in the vertical, i.e. the y slot, is now the x-axis. So you do have to adjust your thinking a little bit, but you can use these graphs as a nice tool to help you convert it to polar. While I am going to use this graph, I am still going to make a table of values just to help us out, because making a table helps. Again, we don't make tables when we're just thinking about graphing in rectangular, because we know the parent graphs, we should not be plotting points. But when we are working with polar, there are just too many parent graphs to memorize, and the transformations for them are fairly complicated. So just for purposes of this class, we use points. Okay, so let's start with theta equals 0. R is clearly 0. And I'm just going to plot out some points here over here on our table first before I even bother with the polar graph. At pi over 6, theta is pi over 6, that's right here. R is 2, and we can check these all computationally just by plugging in different values for theta into the formula. That is how I checked these beforehand. But if we have the graph, sometimes it's a really nice tool to just look at to see what's going on. At pi over 4, right here, we can see that it crosses the line square root of 2, so our r is going to be square root 2. At pi thirds, we're going to hit 0 right there. And at pi halves, we're going to hit -2. So look, we have this so far. Let's see what of the graph this just little piece gets us. So theta equals 0, r equals 0, that is just at the pole. Didn't matter what our theta was at that point. We knew that r was 0, so it did not matter what angle theta we were at. We just know it's going to be at the pole. Okay, then at pi over 6, r equals 2. So we rotate, we go out to 2. So we're going out to this line here of radius 2, this circle, and then we rotate out pi over 6. So our point is going to be right here. That's going to be our second point. And then at pi fourths, we are at square root of 2. So we go out to this radius of square root 2 and rotate around pi fourths. So our point is going to be right here. And then at pi thirds, we are back at the pole, which is at 0. And then at pi halves, we have radius of -2. So we go out -2 like that. We go 2 in the opposite direction, in the quote unquote negative theta direction, and then rotate around pi over 2. And so that's where that point is. Okay, so what does this graph look like so far? Well, this graph is going to kind of end up looking like a flower, and we'll see why. Notice so this is what the shape of the graph is going to look like, just right there. And what part on our axis does this encompass? This is from 0 to pi thirds. So that is right there, is this petal right here. And we do call them petals. That is a math word. These are called petals. That is the first bit. And notice it's a little curvy because the points ours start increasing really, 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 really sharply, just like they do here. And then they start softening as they get closer to pi over 6. They start increasing a little bit less. So I can actually draw this a bit better over here. It'll look more something like that. Just drawing that a bit better. And then same thing happens. They start decreasing a little bit more slowly until they're very sharply decreasing until they're back at 0. So these are going to end up being petals. And we'll address this point down here, the pi over 2 comma -2, once we have some more points surrounding it. But that's what this is going to start off by looking like. And I will draw it. There we go. That's not very good. Cool. All right, let's keep going because I don't think we have all of the graph here. And even if we do, it's always good to just keep going until you're sure you've covered all the points and you're not repeating yourself yet. So let's just keep working with my nice unit circle angles because those are pretty much all you're ever going to really need for these because you're doing them by hand. So let's just keep going. The next unit circle angle that's logical to think about is 2 pi thirds. On the graph that's right here, back at 0. Okay, so we know at pi thirds, the graph is at 0, and then at pi over 2, we go down to -2, and then at 2 pi thirds, we're back at 0. That is this portion of the graph right here. So even though we only have one key point down at -2 comma pi over 2 down here, it's still going to be a petal shape. It's still going to look like this. And so that is this portion of the graph. It's always just good to know these are going to have petal shapes, and that is because it is the entire portion of that curve down there. That is not something you'd know just from plotting the key points, but that's something you should always, always, always keep in mind with these. It is that if we don't have an added constant at the end, these are going to end up like petal shapes, and we'll see another example of this that may make it a little bit more clear why when we have more key values to look at. But these are always going to have this kind of flowery roundish shape. And if you ever want to check, you can use your calculator to plug in some more values in between them just to check. But anyways, let's keep going because we may not be done yet. What's the key angle after 2 pi thirds is 3 pi fourths. Looking on my graph at 3 pi fourths, we are at square root of 2 for radius. At 5 pi over 6, we are right here, back at +2 for a radius. And then at pi, we are back at 0. Okay, because I went from 0 to 0 again, I think I have another one of my petals done. So let's draw that out. 2 pi thirds, we're at 0. At 3 pi fourths, we have a radius of √2. So we go out to +√2, rotate around 3 pi fourths till we land right there. 5 pi 6, we have a radius of 2. So we go out to a radius of 2 and rotate around 5 pi sixths. again, remember that this is not always rotating around to the angle 5 pi 6. It's just rotating around 5 pi 6. If we had a radius of -2 and then 5 pi 6, we would have to just rotate 5 pi 6, which would land us at 11 pi 6. It doesn't always land us at the angle 5 pi 6. And that's in the case when we have a negative radius, but when we have a positive radius, it does. So always just keep that in mind. You're not rotating around to the point, you're rotating around that many radians. Okay, so keeping that in mind, the final point we have is pi comma 0. So we're just back at the origin. So this is going to be another petal like this. Where is this on our rectangular graph? That is just here to here. So on our graph over here, that's just this loop right here. Cool. Now let's keep going and see what happens. The next logical angle is 7 pi 6. And on our graph, we can see at 7 pi 6, we are down to -2. So what happens when we try to plot this point? We'll go at a radius of -2 and then rotate around 7 pi 6. So there's 6 pi 6. And then there's one, what the heck? 6 pi 6, and then one more to 7 pi 6. We've already plotted this point here. So we may just be repeating ourselves at this time because now we're going out from the origin up to here. Let's do one more just to check. Next angle to check would be 5 pi 4ths. At 5 pi 4ths, here we are at -√2. So let's check to see if that point's repeating itself as well. Okay, so we go out to -√2, and then we rotate around 4 pi 4ths and then 5 pi 4ths. Yep, we're repeating ourselves at this point. So this is the final graph. Once you start repeating yourselves like that, retracing over petals you've already drawn or retracing over lines you've already drawn, you're done. Again, you will hit the pole. Oopsies. You will hit the pole multiple times in the center. You're going to hit the center several times because that's just how this works. But if you start repeating points like this, come on, like this over here, you are done with your graph. It's just like with the rectangular coordinates, you're going to start repeating yourself. So you are done at that point. Now, again, notice this is repeating itself. So this portion right here is going to follow the orange line, and then this portion here is going to follow the pink line, and this portion here is going to follow the green line. But one misconception people have with these is that it starts repeating, after the period, just like rectangular coordinates. That's when things start repeating. That is not the case here. If we solve for the range of like how to graph or the period on the rectangular coordinates, we do the inequality 0, and then 3 theta, and then 2 pi, and we'd solve for theta so that theta would be between 0 and 2 pi thirds. Notice that does not happen here because we don't start repeating until after we cross pi. So even though we know it's going to start repeating and it's going to be our intuition to be like, hey, it starts repeating after the period. No, it does not in this case. So for polar, you have to keep going until you see repeating. You cannot just use the period as a benchmark for that. I know I've been guilty of doing that in the past, but while that inequality up here is great for when you're graphing in rectangular coordinates, do not do it for polar coordinates. Questions on this graph down here? Okay. Let's do 2 more examples of these just to get a better feel for how they work. And then we will be actually done for the semester with content. Okay, so we're not given that nice graph over to the side here, but we still want to graph r equals -3/2 cosine 3 theta by plotting y equals -3/2 cosine 3x. So you can do this. I will say you don't necessarily have to do this, but it can be helpful just to sketch out the graph to kind of see what it looks like. So I'll do that, and then I'm just going to go ahead by making a table again. So how do we graph this? Well, we know the amplitude is -3/2. So our graph is going to bottom out at -3/2. And it's going to have peaks over here at +3/2. To get our period, we are going to use that inequality 0 is between 3x and 2 pi. So x ranges from 0 to 2 pi thirds. So the period of the graph, we're going to stop at 2 pi thirds for one full cycle of negative cosine. So it's going to look something like this, where this right here is the 0.2 pi thirds. And then halfway between that is going to be this peak right here. So that's at pi thirds. And then halfway between each of these, it's where it's going to intersect the axis. So at pi sixths and pi halves. Again, this is useful for some people. It is not always useful. If a question on a homework or an exam does not specify that you don't need to plot this like this, you don't need to plot it. But sometimes it can be helpful just for like color coding and thinking about, okay, why is the shape of the graph the way it is, etc. Okay, so now that we kind of have an idea for what the shape of the graph looks like, let's try to draw it in polar coordinates. To do that, I'm again just going to start by making a table of angle theta and r. And when you don't have a nice graph to look at, the best way to do this is just to use your unit circle knowledge and substitute things into the equation. So like for theta equals 0, I would solve y equals negative 3/2 times the cosine of 3 times 0. This ends up being negative 3/2. And again, I'm not using anything that you wouldn't be able to know using unit circle knowledge to do these. Theta is pi 6. That would be solving y equals negative 3/2 cosine of pi halves, because 3 times pi 6 is pi halves. This is 0. I'm just going to get a couple values written out before we start actually plotting them. For pi over 4, we actually get negative root 2 over 2 times that negative 3/2 in front. So it's this nasty value 3 root 2 over 4. We probably won't use this for plotting, but it may be a good benchmark just to kind of see-ish what the shape of the graph will look like. If we wanted to get a decimal approximation of this, that might be helpful just to see, okay, approximately what is our radius at this point? Where should we be lying? Just as a good intuitive check. Pi thirds, we get 3/2, and at pi over 2, we get 0. Okay, we have a 0 to 0 here, so it looks like we may have a pedal or something to work with, so let's try plotting these. Theta equals 0, so we don't rotate around at all. We know we're going to be on that line. Our radius is negative 3 pi halves. So we just go out, let's call this 1 and this 2. So we just go out negative 3/2, and that's right here. I think I said 3 pi halves. It's just negative 3/2. Cool, it's our first point. At pi 6, we have a radius of 0. So rotate around pi 6. We don't even need to think about that because we're just at the pole. Okay, pi fourths, we are at 3 root 2 over 4. I don't remember what that is when I plug it into my calculator. It's like 0.75 times 1.4. So it's a little more than 1. So it's just greater than 1, but it's less than 2. So we can just kind of think about, it's between 1 and 2 somewhere-ish, but it's also a little bit less than 3/2. Again, if you need to, you can plug that into your calculator to get approximation, but I'm just going to ignore it for now. If we need it later, we can use it. At pi thirds, we are going to have a radius of 3/2. So go out a radius of 3/2 and then rotate around pi thirds. Cool. Now we're getting somewhere. And then at pi over 2, we're back at 0. So it doesn't look like we have much to work with here, but we actually do. So we know we're starting here, and then we're going to the point 0. That point of the graph is from 0 to pi over 6. So that is this portion right here. So it is curved. We are starting with R values that are increasing, but a little bit slower. And then the R values start increasing more as we get closer to 0. So this is going to have the flower petal shape like this going in there. That is that portion of the graph. It's not a full flower petal because we started here and we're just going in, but we may finish the flower petal later. We don't know what goes over there, but we'll see later. Okay. And then we know from pi 6 to pi thirds, we get from 0 to 3/2, kind of in the flower petal shape. Again, we know pi fourths were somewhere in this region down here. So we know we're going to pass through that in some way. So that looks like this. and then back down at pi halves, we're back down to 0. So we make a full, that is not drawn very well because that is not at 3 halves. That's a lot better. So we know we go out like this and then round back into 0. And that, try to highlight it. That's from pi 6 to pi halves. So that's this portion of the graph. We go like that. That's again, why those values for pi fourths aren't super important and why we don't need their exact values. We only really care about the peaks and troughs of our graph in rectangular coordinates. So these points, because those are going to be the tips of the flower petals usually. But we don't super care what the pi fourths is. It's just helpful when you're first starting out learning the shapes of the graph to say, hey, about where am I going to land here? All right, this graph does not look like it's done in any sense to me, so let's keep going. Continuing on with more theta values, at 2 pi thirds, we are at -3 halves, I believe. Yeah, because this is 2 pi thirds, that is where the period ends on our graph, but as we'll see in a minute, that is not where the polar graph is complete, so we can't just stop when the period's over. So let's keep going. And I guess I'll draw this out a little more just to finish with what our color looks like. That's going to be at 5 pi 6, and this peak over here is going to be at pi. Okay, next point at 3 pi fourths, we are going to have this weird -3√2/4. Again, not one we're going to necessarily have to plot, but that may be helpful to guide the shape of the graph. Running out of room, so I'll just keep going over here. Next angle is at 5 pi 6. When I plug that into my equation, I see that it's 0. And on the graph, that is where it crosses the now theta axis. It's not, it used to be the x-axis, now it's the theta axis. All right, and then at pi, when we plug pi in, cosine of 3 pi is 1 times -3 halves is -3 halves. Okay, we have some more to work with here. Let's keep going. So 2 pi thirds is -3/2. So we go out a radius of -3 halves, and then we walk around the circle 2 pi thirds. So there's 1 pi third, and then there's 2 pi thirds. So we end up right here. Again, notice I did not walk around to the angle 2 pi thirds. I went out my radius and then rotated around from where that radius started 2 pi thirds. So that's where that one's going to be. Then at 3 pi fourths, we have this -3√2/4. We can think about that's probably going to be like right here-ish. And then we walk around 1, 2, 3 pi thirds. So that point's going to be like here-ish. Again, it does not matter exactly, but it gives us a good idea that, hey, 5 pi over 6, we're back to 0. So this is probably going to be another flower petal. Maybe looks something like this. So back to 5, we do that, back to 5 pi over 6, that is this portion of the graph. Okay, looks like we may be almost done. And that is true because when we get to pi radians, we go out from this point at 0 to -3 halves. So we go out to, oh, not -3 halves, it's +3 halves. That's my bad. This is +3 halves. So the cosine of 3 pi, that's my bad. The cosine of 3 pi is -1, and then times -3 halves is +3 halves. That's my bad. Okay, so we got to the radius of 3 halves. So that's right here, and then walk around pi radian. So that's going to be that point right there. That means we walk from 0 out here. And that petal looks a little more complete now. So that is going to be this little chunk right there, where we walk out like that right there. This graph is complete at this point. We can do a check if we keep going by looking at, oh, what happens at 7 pi over 6 and 3 pi or 5 pi fourths. We could keep going just to check to make sure that these points do indeed repeat, but they do. We have a complete graph. We are good to go. There's nothing else really to check here. Note that even though this example and the one we did before were flowers with 3 petals, not all graphs will have exactly 3 petals. Not all polar graphs will maintain this exact shape. So if you see 3 petals, that doesn't mean stop. Some graphs only have 2, some graphs don't have any, some can have 4, 5, 6, etc. So the rule of thumb is just to keep checking as you go, and once you think you're done, do a couple more points after that just to check to make sure that indeed the cycle does start repeating. So that would start going like that. Any questions on how we did this one? Again, this is just essentially a matter of plotting key points and then following as the values of theta increase, following them around, drawing them. It really helps with these sometimes, just to be sketching as you go and not just make the table and try to draw from there, because it can be easy, especially with negative radii like this, to forget what order the points were drawn in. So as long as you make sure you're connecting the dots in order of increasing thetas and that they're maintaining this kind of rounded shape, you're good to go. All right, let's do one more and then we will call it for the day. This one's a little different. It has what we would call a vertical shift now in rectangular coordinates. We want to graph r equals 2 plus the sine of 2 theta by plotting points. Okay, so we don't even really need to draw the graph at this point in rectangular coordinates. We can kind of imagine what it would look like. It has an amplitude of 1 and a vertical shift of 2. So the midline would be up here at 2. And we know it has an amplitude of 1, so it's never going to go above 3 or below 1. And it has the shape of sine, so it's going to do something like this. It's never going to touch our x/now theta axis here, which is something that matters. That is important, and we'll see why. But it never touches that down there. And the period is, I think, is going to be pi. So this point right here is going to be at pi. Right here, the midline is going to be pi over 2. That's going to be 3 pi fourths, and this is going to be pi fourths. Okay, so the instructions suggest that we just look at multiples of pi over 6 for a little bit, and then start just looking at multiples of pi over 4 to make our lives easier after that. So let's just follow that guidance, see where it leads us, and see what our graph looks like. So just doing what we have been doing, making a table of points, theta and r. Start at theta 0 because that's the best place to start. If we plug 0 into the equation, r equals 2 plus sine of 2 theta, the sine of 0 is 0, plus 2 is 2. So our initial point, theta is 0, and r is 2. So we go out radius of 2. Let's call this point right here 2 and this point 4. Since we know we're going to hit things as much as 3, we need a little bit more axis room for that. So we'll go out that, rotate around the angle 0 at radius 2. So that point's going to be right there. All right, now it's suggested we do some multiples of pi over 6. So let's do that. We plug that in. The sine of pi thirds, which is 2 times pi over 6, is going to be root 3 over 2 and then plus 2. So it's going to be 2 plus root 3 over 2. So let's think about what this number is. Root 3 is a number, I think it's like 1.7 or something divided by 2. I know that the square root of 3 is between 1 and 2. That's all I know. So I know this is going to be a number that's around 0.5 to 1 or something, plus 2. So we know it's going to be about 2.5. We know it's going to be somewhere like here-ish. Again, we don't really know where it's going to land, but you'll see it doesn't really matter. We only are going to need more important points once we get an idea for the shape. We're just going to ignore these nasty multiples of pi over 6 altogether. Let's keep going. When theta is pi fourths, plugging pi fourths into this equation, we get 3, because 2 times pi fourths is pi halves. The sine of pi over 2 is 1 plus 2 is 3. Just going a little bit more, doing a couple more of these multiples of 6. At pi thirds, the sine of 2 pi thirds is root 3 over 2 plus 2. So 2 plus root 3 over 2. Let's plot these 2 recent points I just did. So at pi fourths, we have radius 3. So we go out to about 3 and then rotate around pi over 4. That's going to be like right here. And then at pi thirds, we're going to have that weird wonky value that's somewhere in that radius. We don't really know. And then what happens at pi over 2? If we plug pi over 2 into the equation, the sign of pi, which is pi over 2 times 2, is 0 plus 2 is 2. So at pi over 2, we have a radius of 2, so that's right there. So far, our shape kind of looks something like this. That's kind of what we have so far. We don't really know where it's going yet, but let's keep going. So at 3 pi over 4, when we plug that into our equation, we get 1. And when we plug pi in, we get 2. Now just kind of ignoring those nasty multiples of pi over 6. So at 3 pi fourths, we have a radius of 1. And then at pi, we're back to a radius of 2. So we kind of have this weird shape going on here. Let's keep going, see how this ends up. I'm going to just ignore the multiples of pi over 6 now, just because I don't think we really need them. So let's next look at 5 pi over 4, ignoring 7 pi over 6. 5 pi over 4, we have a radius of 3. At 3 pi over 2, we have a radius of 2. This is just plugging these values for theta into the equation and seeing what r we get out. 7 pi over 4, we have a radius of 1. And then at 2 pi, we have a radius of 2. So 5 pi over 4, we're out at 3. At 3 pi over 2, we're out at 2. 7 pi fourths, we're down to 1, and then we're back out at 2. So that shape, we can imagine, kind of looks something like this. It's a little bit like a bean. It goes out to meet the 3 and then back into the 2 and then dips to the 1 and then back out to the 2. So this one doesn't have a center. This one does not look like a flower at all. I'm just going to try to fix the shape so it looks a little better because these pi over 6s were not great. Kind of looks like this. It's a little bit of a bean shape, and this is actually the final shape. You can imagine if we kept going again and checking, okay, what about 9 pi over 4? We would be back out to 3, and then at 10 pi over 4, which is 5 pi over 2, you back down to 2. You can imagine that's how this would keep going, and you can verify that with calculation. But this one does not look like a flower. It has this little bit of a bean shape. Why is that? Well, that is purely because right here of this vertical shift. Because of the vertical shift, we never cross the theta axis when we're looking at the graph in rectangular coordinates. We never go to the pole. We never go to that point where r equals 0. So we never cross the point r equals 0 here either. We never cross that x-axis. We avoid it completely. We avoid the theta axis entirely. We avoid those points where r equals 0. As a result, in polar, we never touch the pole because we never touch the quote unquote pole in rectangular coordinates. So this one might be a little strange looking after, hey, this one was a flower and this one was a flower. Neither of these had a vertical shift and they intersected the x/now theta axis many times. So at those points is when we created petals, is when we knew we had a 0 to 0. We knew that's when we had a petal, when we had a complete full rotation around. That never happened here. Notice we only ever had positive values for r, and that's because looking at our rectangular graph over here, we only ever had positive values for y/what we're now calling r. So that intuitively makes sense. Again, this is why we're not talking really about parent graphs in this class, because there are so many of them. And even just something as simple as a vertical shift like this, while all it did in rectangular coordinates was move the graph up, it completely changed the shape of the polar coordinates. So that's why we don't talk about parent graphs in here, because there are so many of them. It is a fun activity if you're ever really bored to just go on to Desmos or something and try graphing different variations of this. Like, I think like sine of 7 theta, for example, is a flower graph that has seven different petals because there's a 7 in there. I don't know. There's a bunch of really cool different shapes that change just depending on slight teeny little changes to the equation. And I think they're cool to look at sometimes. So if you're ever bored or curious, you can go do that. But just know we don't need to talk about parent graphs in this class. The only thing I'm going to care about is if it asks, be able to at least sketch the parent with some key points, and then be able to evaluate by hand values for this just using the unit circle. I'm never going to ask for values plotted outside of familiar unit circle values. Are there any questions on graphing these? Hopefully it is just a matter of plotting points in the correct order and drawing the dots in the correct order, making sure you're always moving around counterclockwise. If you're drawing clockwise, something's going wrong because the angles move around counterclockwise, so you should only always be drawing counterclockwise. Okay, that is actually it for content for the semester. So we are done with the course. that is it. That should be the last page in your course packet. So yay, that's awesome. In the next few days, I would focus on trying to identify areas that you still need help on and either going through Alex with those or email me. I'd be happy to do examples either on review day or just meet with you on your own. I'm going to make myself completely available for the rest of this week. If anyone needs help, just shoot me an email. But otherwise, this is all we are going to cover. So you should now be fit to do the Alex and the written homework that is due tomorrow night. Again, if you need a little extension on that because of the exam Thursday, that's okay. I just didn't want to have the exam and the homework due the same day. So if you need that, let me know. But otherwise, you should be able to do the homework by Wednesday. I don't think I made it too terribly long. There's one of these on there, an example with vectors, and then I think a vector applications example, and that's it. But otherwise, let me know if you have any questions. Otherwise, have a wonderful Tuesday, and I will see you all for review tomorrow.